Okay, I think that we can start with the first session for this IMAV conference. We're going to begin with our first presenter, who is Dennis.
Yes.
And he will present the flight code convergence, fixed wing, rotorcraft, and hybrid vehicles. Please,
Okay.
Dennis, start with the conference.
Okay, I will start. Okay, thank you all for attending this presentation online. Together with two other researchers, Ewout and Bart, we wrote a paper about flight code convergence. And basically what we try to answer in our research, if we could fly three totally different types of drones that you see now on the slides in one code base. So what is this presentation about? We'll first introduce the subjects. I will discuss the test platforms we use for this research. My colleague will introduce you to the INDI control. The results will be presented afterwards, and we'll end with a conclusion. First of all, there are already current solutions to fly fixed wings, hybrid drones, and rotorcraft drones. But there is no single code base that can basically fly all drones. For example, you have already solutions at PX4 or RDPilot, but basically what is happening between forward flight and hover flight is basically that the controller is changing inside. In Paparazzi, you already have the hybrid code where we can fly hybrids on, and we wanted to extend this hybrid code such that it can also be possible to fly fixed wings and quad rotors on this code. So we tried to fly all those drones at a single code base, such that the code is easier to maintain and the chance of producing errors is smaller. We did this to implement the flight envelope protection in the Paparazzi hybrid codes on pitch, roll, and airspeed. So throughout the paper, we defined a body axis system. Basically, it's a right-handed system in which the z-axis is the opposite way of the thrust vector. So that means that for the flying wing, for example, in forward flight, it will always fly approximately at -90-degree pitch. So basically, the body axis system is defined in hover for the three platforms, where but the fixed wing cannot fly in hover. So actually, you will see that it always flies around -90-degree pitch. The first test platform we use for our experiments is the Nader Drone that has been developed by the IMAV lab. It's a hybrid tail-sitter UAV with 12 motors and 8 control surfaces. The flight envelope is protected in pitch and roll for this hybrid drone. Secondly, as a fixed wing, we use the Paradisco. It has one motor and 2 elephants, but pure yaw control was not possible because we don't have a control surface to control this. You see that additional to pitch and roll, we also limit the airspeed flight envelope to be bigger than 10 meters per second to make sure that enough flow is streaming over the control surfaces. Finally, as a multirotor, we used the Parrot Beeble 2. It's just an X rotor with 4 motors, and the flight envelope was limited in pitch and roll. Now my colleague will introduce the INDI controller that was applied on those platforms.
Hi, my name is Ewout Smeur, and I will tell you about the control method that we use to control each of these 3 platforms. And in fact, it's the same control method. We used incremental nonlinear dynamic inversion to control each of these 3 methods. The abbreviation is INDI. And it's really a simple control algorithm. So here on the screen, you see the model that we used. So it's just, let's say we have an input delta nu, which we relate to the output delta nu through a control effectiveness matrix G. We can do this for angular acceleration, and then we're mapping motor and servo commands to a change in angular acceleration, P dot, Q dot, and R dot. And we can do this for linear acceleration. In that case, we're mapping changes in roll, pitch, and thrust to the linear acceleration of the vehicle. And that means that every drone, each of our 3 drones, will have a different control effectiveness matrix. And this is basically a Jacobian matrix, which contains partial first-order derivatives. So the matrix will be different, but the control structure will be the same. And the strong point of this control method is that it's very good against disturbances and unmodeled dynamics, because we are measuring angular acceleration or at least deriving it through the gyroscope measurements. We're measuring linear accelerations, so we're very fast in compensating forces and moments that generate linear accelerations and angular accelerations. So again, the matrix G depends on the platform, but the control structure is the same. Now there's two extra things that we need to take into account. For the outer loop, so the control of the linear accelerations, the heading psi is free. And that means that we can do something useful with it. We use it to minimize the side slip, which is important for the fixed wing and the hybrid drones. We do this by using a feed forward term based on the roll angle and a feedback term, which comes from the accelerometer in the y-axis, because that is related to the side slip angle. And that means that we do not need a side slip sensor. Obviously, the quadrotor does not need this side slip compensation, but it doesn't hurt either. The second thing is that we want the fixed wing and the hybrid to make a nice turn in forward flight if they have sufficient speed, instead of stopping and turning around and gaining speed again. We do this by forcing the drone to maintain its speed if it already is at high speed and wants to, and the desired speed is still above a certain threshold. In that case, it's commanded to accelerate sideways, which will lead to a roll angle and make a turn to resolve a velocity set point error. All right, to summarize the control structure, we have two INDI controllers, so one for angular acceleration and one for linear acceleration. And because that's basically a feedback linearization algorithm, the loops around these INDI controllers can be proportional linear controllers. So the differences between the platforms are in terms of the control effectiveness. So those are parametric differences. In terms of the gains of these attitude and angular rate, velocity and position controllers, and in terms of their limits. Most notably, the fixed wing has a limit for the airspeed, and because if it would fly slower, it would stall. And the Rotorcraft has much lower pitch and roll limits. But all these differences are parametric, and the control structure is the same for each of these vehicles. All right, so now let's see what Dennis can tell us about the results.
Okay, thank you, Ewout. So we'll now go to the results. So basically, for every platform we've introduced, we flew a route. First of all, I will start with the fixed wing. You can see that fixed wing followed target lines, and you can easily see that it managed to do that. Secondly, the Parrot Bebop 2 was also able to follow target lines. But additionally to that, it could also stop at a position and hover above this, as you can see now indicated by the red circles. If you move from hovering at the target position to line following, you can see that the drone first perpendicular flies to this line and then joins the line and flies over this line in hover, as the Parrot Bebop pitch and roll is limited. Finally, we also flew a route with the Nader Drone, the hybrid drone. And you can see, if you compare it, for example, to the Disco, that the radius of the turns is bigger. This drone also has a higher airspeed and lower roll limits. So that's the reason why it was less accurate on the line following. You can also see the target positions in the flight plan of the Nado drone. So basically, this drone can move from forward flight to hover flight and enter the target line again, as is indicated by the red circle. Let's move to the results in the vertical guidance. So for every platform, we performed a step input on the altitude, on the commanded altitude. First of all, I will discuss the flying wing, the Disco. We can see some drops in altitude, and after further analysis, it was it seems to be appearing in the turns. This is because we don't have full yaw control in this drone, and for that reason, we don't have we miss one axis of control, and as a result of this, it drops altitude in the turns. But if you look at the step, it is able to climb and descend according to its step inputs with accuracy of about 10 meters. Secondly, the Rotorcraft, the Parrot Bebop 2, was able to track its altitude set point really well because the motors, the altitude can directly be controlled by the 4 motors. Finally, we also see a step descent for the Nader Drone, and it was also able to follow its step descent, but you see a drop and a gain in altitude, and this corresponds to the moment that the Nader Drone actually transitions from forward flight to hover and vice versa. So we see a drop in altitude when we go from forward flight to hover, and a gain in altitude when we go from hover to forward flight again. Now we evaluate the flight envelope limits in terms of pitch and roll. So you see the plots for all 3 types of platforms, and you see the flight envelope limits indicated here. So first of all, for the fixed wing, it can be seen that the flight envelope, the pitch and roll stay within its flight envelope limits. You can also see that the pitch of this drone is constantly about -80 degrees, and that's because in the reference system we defined to fly, to generate lift with the wings, we have to fly at about -90 degrees of pitch. We can also see that Bebop stayed within its flight envelope limits. And for the Nader Drone, in terms of roll, we see that it slightly exceeded its limit. And another thing you can see in the Nader Drone plot is actually the increase in pitch during transition. And I will come back to that transition later. Now we also had an airspeed set point for the fixed wing and the Nader Drone. For the fixed wing, the Disco, we see that the tracking of the airspeed was about 1 meter per second accurate. For the Nader Drone, we see something, we see the transition in the airspeed plot, indicated now at the red lines. Actually, at the position of the red line, the Nader Drone transitioned from forward flight to hover flight. And in this case, the airspeed sensor gives 0 meters per second because it's pointing upwards in this case. I will come back to the transition later. Here you can see that in a hover flight, we moved the hover waypoint around, and you can see that the Nader Drone actually gains airspeed again because we are pitching down at this moment. What I already said, I will zoom into the transition of the Nader Drone. First of all, what I already discussed, the loss in altitude when we transition from forward flight to hover, as you can see. Secondly, we moved the waypoint around, and there you can see that the pitch is decreasing, airspeed is increasing, and altitude is increasing. So I would like to conclude this presentation. We demonstrated the feasibility of unification of control for fixed wing, hybrid, and rotorcraft during our research. By implementing some flight limits to protect the flight envelope of each type of drone. The side slip control for the multirotor is not always useful because a multirotor you want to point at sometimes in a specific direction to make some recordings, for example, if you have sensors on board, and we don't need a side slip controller there to reduce drag. So for future work, we propose to improve the tracking performance for the altitudes for the fixed wing and forward flight, and for the hybrids during transitions. And the position accuracy of the quad rotor can also be improved. We also want to test this controller in the future on quad planes and helicopters. So this was our presentation, and I would like to answer your questions if you have them.
Thank you very much, Dennis. Do you have time for questions? Is there a question? Do you have a question? I have one question, Dennis. How do you implement your controller in the Parrot, for instance? Do you turn off the internal control of the system?
Yeah, basically you can hack those Parrot drones. So we are using a paparazzi UAV. I think there's just a Linux computer running on it, so you can access the drone using a telnet connection, and you can basically flash your paparazzi software on those Parrot drones. So currently in paparazzi UAV, you can flash the Parrot Disco and the Bebop 2. In our paper, we also made a reference to the branch we use. So if you want to test this code yourself, it is ready to fly. So yeah, I think it's a good autopilot and software, because yeah, you can flash it on a lot of platforms.
So for instance, in the Parrot, what are your control signals? The PWM that you send to the motors?
I think there is indeed a PWM driver in the software. I think you can just access the inputs on the Linux chip. I think you can just control drivers to some inputs there, and you can control the motors using that. But that's like really, if you go really deep into the drone. For this research, this was already set up, and we basically sent so-called paparazzi commands to the motor that will just do the conversion from a command defined in paparazzi to a motor command.
There is another question, Dennis, from Matthias. He asked, which sensor do you use to measure position and altitude and the accuracy of these sensors?
I think Ewout can answer this question.
Yeah, we used a GPS sensor on each drone to measure the 3D position. And additionally, we had a barometer also on each drone for additional information on the altitude. Does that answer your question?
Matthias, I think that yes. We have another. Do you have another question? Public.
Maybe you can say something. Oh, go ahead.
So you use the same dynamic model for all these aircraft? You just change the input matrix? That's the approach that you use, that you follow?
Basically, it is, yeah. And we have just a normal equation of motion for a rigid body, and the controller actually neglects the influence of the states on the linear acceleration and the angular acceleration. But because we're looking at changes in the acceleration and angular acceleration, and we are measuring the angular acceleration at this point in time and the angular acceleration at this point in time, and we are measuring the influence of the state through this feedback. And the error that we make by neglecting changes in the state that have an influence on the forces and the moments is therefore relatively small. And that means that we can use really the same control structure without a complex model for the hybrid drone, for the fixed-wing drone, and for the rotorcraft.
Thank you very much. It looks interesting. So I think that we now have to switch to the other presenter. And I think that people cannot clap, but I will give a small clap. So now we go to the paper 27, I think, yes.
Yes, so I think my camera just stopped working, so I'll just start the presentation.
Okay, yes, it's okay.
Okay, so hi everyone. It's my pleasure to give a presentation about nonlinear model predictive control for improving range-based relative localization by maximizing observability. So first, let's look at the background. Okay, so first I want to show a video. So we designed an autonomous swarm of micro air vehicles that use onboard relative localization to do the swarm flights. So here, as you see, we control the leader by a remote controller, but the two followers estimate the relative positions with respect to the leaders with the onboard command filter, and then First they will have 20 seconds initialization procedure to get the relative localization converge. So the two followers has the random velocities within 1 meter to avoid the collisions, but also to get the estimator converge. After 20 seconds, they will do the formation flights with a constant relative positions to the leaders. So we fly the leader manually through the hull, and the two followers can follow it with a very high accurate positions. And this is the indoor test, and this is the outdoor flights. So now let's get back to the slides. So this multiple macro vehicles, they are fully autonomous. That means they can fly without the GPS, neither the motion capture systems. They are low cost and lightweight with only 33 grams for each drone. And also the hardware are open source. So our swarm code can be run directly on these commercial drones for this demo. Sorry. So the details for the onboard localization is shown in this figure. The onboard camera filter takes the MU optical flow and the laser sensor data to calculate the body frame velocity, body frame yaw rate, and its height, and attitude roll and pitch. After rotation, each drone can exchange the velocity, yaw rate, and height with ultra-wideband to other drones. At the same time, they can receive the relative information from other drones. And then the onboard camera filter can calculate the 3D relative positions and the relative yaw between any two drones. So the second part is the problem. The camera filter, the problem for this camera filter is the relative states. There are three, X, Y, and relative yaw. But the measurement is only the distance. The ultra wideband only gives the one-dimensional distance measurements. That means this system is weakly observable. And also the kinematic model of the relative states is related to the X and input. Input is the velocity of both drones. So the kinematic model is nonlinear. So therefore, there's an observability matrix to determine if the system is observable or not. That means if the determinant of this matrix is not zero, then the system is observable. We can use the distance measurement to calculate the 3D relative positions between two drones. If it's zero, then we cannot calculate the relative positions. For example, when they both hover, the distance does not change. So we cannot let the two drones to estimate the relative positions between them. So how can we design a proper control inputs like the velocity inputs for both drones to maximize this matrix determinant to get a better observability? So we decided to use the nonlinear model predictive control because this controller can handle both the constraint cost function and also the desired relative positions between drones. So here's the detailed design. The controller consists of two sub-cost functions. The first part, it is used to maximize this observability matrix determinant to let the system has a better observability. The second part is to minimize the relative positions error between two drones to achieve a multi-drone task, like the formation flight. And also we consider the constraints. The first constraint is the prediction model satisfies the previous relative motion model between two drones, and also we set a limitation for the relative states and also the safe distance between two drones. Also the velocity for both drones, they are also limited. Here we set like 2 meters per second. This control to solve this nonlinear optimal control problem, we decided to use Arcado. It is an open source, fast, embedded solvers for nonlinear optimal control. Because it supports Python interface, so we can use it directly to control the crazy fly quadrotors from computer. So in this solver we set the prediction steps as 50 steps, and also the stop criteria is error is this, and also we decided to use these settings for this Arcado program. So here's the testing results. So the red dot means the estimate relative positions of the second drone. The blue dot means the ground truth position of the second drone. So the left figure means the localization convergence with the random control inputs, like the random velocity inputs. The red figure is the test with the model predictive control inputs. So as you can see, the red one with optimal control, it has about 5 seconds to get the relative positions converged, while the left one with the random input, it takes about 9 or 10 seconds to get the relative localization converged. And also after convergence, the optimal control can give a smaller estimation error compared to the random inputs. So this is the figure for the previous test. For the three-dimensional relative states, we can see in both x, y, and the relative yaw, the optimal control has a faster convergence time and also a less localization error for long term. So another interesting point we found is that this optimal controller actually gave the velocity inputs for both drones with equal phase, with as maximum velocity as possible. For example, here we set the maximum velocity as 2 meters per second. So both drones try to get the maximum velocity with equal phase. This can actually excite all dimensional motions. So the relative positions for all axes can get converged by this control input. And also we give some quantity analysis of the localization convergence time. So here, the red figure means the optimal control has a short convergence time compared to the random velocity input. So here you see for all three-dimensional, the convergence time is smaller than the smaller for the optimal control than the random input. And also after convergence, the optimal control has a smaller error localization error distribution as a red line compared to the random inputs of blue and yellow lines. So in addition, we instead of only considering the observability, we also has a cost function to set the multi-drone task, like the formation flights. So here, after 15 seconds, the cost function has a non-zero weight, such that this sub-cost function also works. And then we can see this nonlinear model predictive controller can maximize the observability, and at the same time it can also do the desired formation flight. So here's the test video. So after 15 seconds, the follower decided to do the circle trajectory around the leader because of the second cost function of the nonlinear model predictive control. So the conclusion is for the multi-drone localization and control, this nonlinear MPC can maximize the nonlinear observability. It can decrease the localization convergence time and also decrease the steady localization error. This controller can also satisfy the states and the input constraints. At the same time, it can also fulfill the multi-robot task, like the formation flights. Yeah, that's the presentation. So, is there any question about this?
Thank you, Lee. Do we have questions? I have one question.
Okay.
Why did you decide to measure observability through the determinant?
Actually, it is a nonlinear observability theory from the linear derivatives.
Yes,
so,
but you have a matrix.
Yeah, there's a matrix here.
And you are defining a kind of distance of this matrix. And why you decide to use determinant?
Yeah, because if according to the theory, nonlinear observability theory, if the determinant of the observability matrix is 0, then the system has a bad observability.
Yes, it will be observable if the matrix is equal to 0.01. It will be observable if the determinant is equal to 1. So why how you decided that this determinant will measure how strong the observability is?
Yeah, we don't know, but so we think what if we maximize this determinant? How about the influence from this to the localization error, such that we design the cost function with this matrix determinant, and we see in the result that it's indeed improves the localization error.
It works, but I think that you need a better support to use the determinant, because as you have a matrix, you can also compute the singular values, for instance, and probably you can define another kind of measure observability using them. But well, it's a good approach, and it works. We have another question. To run your optimization code, how much time do you need?
You mean the convergence time?
Yes.
It is, here's the statistics of the 30 random tests with different initial positions. So we can see the average time is about, it's between 5 to 10 seconds, the average convergence time.
We have another question from Fermi. Is the results in simulation or real time?
Sorry.
Your results, your simulations are, what time are you using them? Is real time or you are using?
The real time. The control interval is 0.01 seconds in the simulation, and it can run in real time. It is the server runs very fast.
Mm-hmm. Thank you. There is another question. We don't have any other question. Your drones in the first video are commercial drones?
Yes, it is the Crazy Fly Quadrotor.
Okay.
So
mm-hmm.
Yeah, from Big Chris.
And they communicate each other using Wi-Fi or what kind of?
With the ultra wideband, this one, the blue communication sensor to communicate with between every two drones. So
Thank you.
Yeah.
Oh, it's an interesting drone.
Yes. So the ranging communication frequency is about for two drones, it can be up to 300 Hertz. So the ranging distance measurement is very, it's a very high frequency.
Okay, thank you, Lee. I think that
thank you.
Thank you for your presentation.
Thank you for watching.
So let's go to the last paper of this session. It's paper number 1 from Matthias.
Okay.
Okay, Matthias, I think that you can start. We are close to
okay, great. Thank you. In my talk, I will present a model for multirotor drone dynamics and a simple procedure to identify its parameters. And this model is specifically crafted for onboard MPC. In the introduction, I will quickly go over the most used basic quadrotor model and then try to motivate why I would be looking for a new variant. Next, I will elaborate on the model itself, how to gather the data for identification and how to estimate its model parameters. And finally, I will show some results of a free flight experiment with a simulation for different model complexities. So the goal in my work is to enable autonomous aggressive drone flight using onboard nonlinear model predictive control. And in this context, the mostly used basic quadrotor model is one in which the control inputs are the four, well, in case of a quadrotor, 4 motor forces, F1 up to F4. And together we can see them as a collective thrust, and then they also generate torques to orient the body. And the states of this system are the positions, velocity, the orientation, and the body rates. And so here we see the derivative of the position of velocity and the body rates. And I left out one equation here because usually this is one of 3 possible options, depending on how the orientation is represented. Usually this is either using Euler angles, roll, pitch, and yaw. And in that case, the derivatives look like this. Or this is using quaternions, or this is with an expression for the derivative of the rotation matrix itself. And to this basic model, often there's an addition of aerodynamic drag, which is often simplified, for example, in a linear approximation, which they sometimes call the RDRV model. in which D is a diagonal matrix with drag coefficients on the diagonal, and R is again the rotation matrix. A very common simplification is linearization around hover, especially in MPCs is done very often as well, such that the horizontal and vertical behavior is decoupled. The rotation matrix is almost the identity matrix, and the derivatives of the Euler angles are almost equal to the body rates. And lastly, a very interesting way to capture attitude dynamics as closed loop is to, in the linear model, actually represent the attitude dynamics as a torsional inertia spring damper seesaw system. And then the attitude dynamics are governed by this second order differential equation. Another contribution in our work is actually to transfer this idea of closed loop simplified attitude dynamics as a second order model to the nonlinear model, or to a nonlinear model, and so to represent them as simplified linear time invariant dynamics, and to add a simplified battery voltage effect, and also include this linear drag as mentioned above. Now for model identification, there's an extensive list of techniques, great literature, either for white box, gray box, black box models, you name it, time domain, frequency domain, etc. But very often the data gathering here involves a cumbersome procedure in which drones have to be disassembled and separate components have to be mounted on test rigs, or you need very accurate CAD models of the drone to get to the parameters. And then here the contribution is that actually we keep the drone as a whole, and we apply in an outdoor flight very very simple maneuvers in which we excite parts of the system. So actually it's all subsystems, and then the gathered data we can use in a linear in a least squares estimation. And this data is gathered only using outdoor available sensors, so in a realistic application, so no motion capture systems or alike. And like I said, there is no disassembly necessary. So the platform on which we are doing our work is a homemade platform on which we have a flight controller, the Pixar Cube, which performs low-level computations and control, which communicates with a companion computer, an NVIDIA Jetson TX2, which does higher level computations. And then these two communicate over MAVLink using MAVROS libraries. And so what the companion computer sees, because on the model predictive control runs on the companion computer, what it sees is an interface in which it can send attitude references, or a roll reference, pitch reference, a yaw rate reference, and then a throttle input, which is just a number between 0 and 1, which is a measure for how much thrust you want to generate. And what comes out of the system is the orientation, and then also acceleration, velocity, and the position. And so what we are interested in now is how to describe the behavior between these references and what actually comes out. And so what this companion computer sees is the ensemble of the quadrotor dynamics and all control loops that are in the PICSOC or in the flight controller. And so we want to represent these two things together in a simple way, for which we developed a gray box model, a simplified gray box model. And so first, to motivate our proposed dynamic model, I will show some data that we recorded. For example, when we apply a roll step or a pitch step, we see this kind of response. So we have a delay at the beginning, and then we have a response that always immediately reminds me of a second order system. And this is also like the red lines you see is a simulation of a second order system, which generally captures this behavior quite well, approximately, of course. Same for the vertical behavior. So if we apply a throttle step, then we see first a delay and then some first order like behavior. And what also can be noticed in this plot is that for lower battery voltages, the vertical acceleration is also lower, which is why we also include a battery voltage dependency. Next, for the yaw rate, again, globally and approximately, this is captured well by a first order response. And so if we put this together in a schematic, then it looks like this, which is a lot, but don't worry, I will break it down. Basically, the top half is the attitude dynamics and the thrust dynamics, and then the bottom half is rigid body dynamics. So if we zoom in on the attitude dynamics, at first we see the control inputs, which are brought into an input delay. So we assume that communication delay between flight controller and companion computer can be lumped into an input delay. And then we have our second order and first order systems for attitude and for thrust. And then the attitude, the angles we can put into a matrix, and we get the rotation matrix. And then the thrust or the throttle, we can add a thrust gain to get actual thrust. This simple relation that represents battery voltage. And then what comes out is an thrust acceleration, which is actually just the thrust force divided by the drone mass. And these two things we can then use in the rigid body dynamics. So basically we can represent the quadrotor now as a point mass on which 4 forces or accelerations equivalently act. The first one is a thrust acceleration, which we assume to be parallel to the z-axis of the drone's body, so the thrust acceleration. We have gravity working downwards. We have the velocity induced drag, which follows the RDRV model, like I said before, so we loop back the velocity. And then we have lastly a disturbance acceleration, which actually captures everything that's not in the others. So that's also model imperfections, wind disturbance, which we haven't modeled so far, but later on an estimator could, for example, estimate this disturbance. So adding these together, we get an acceleration, integrating twice to get a velocity and position. Now this model has a number of parameters, 12 to be exact, and they need to be estimated. So we have a delay time, we have the parameters for the second order and first order systems. We have a thrust gain, battery voltage exponent, and then the drag matrix D, which contains on the diagonal the drag acceleration coefficients. So to gather the data, we apply present three identification maneuvers that excite parts of this schematic. So the first one, we apply a step input on the roll or on the pitch angle. For the second one maneuver, we apply a step input on the throttle, both for ascending conditions, near to hover conditions, and descending conditions, such that we have all these conditions in our data. And lastly, also a step input on the yaw rate. Now, if we apply all of these, if we repeat these maneuvers for different magnitudes, we get n sets of length n, and then we simulate the system given the inputs and compare it to the data, so we get an error. And actually, we just minimize the least squares between the simulation and the recorded data. And the simulation is done with a fourth order Makuta scheme. So this is actually quite straightforward. And then the results of the fit I actually already showed you before. So we see that we have our delay and then our second order response. For the vertical response, again, we see lower, we see our first order behavior and lower response for lower battery voltages. Also note that on this plot, I'm only showing it for one regime, because if I show all of the measured data, then this plot will not be clearly visible at all. And then for the yaw rate, you see that there are some faster transients here, transient behavior that is not really captured. But again, this is an approximate model because we're trading off complexity against accuracy. And then on a global level, this actually approximated quite well. And then lastly, the drag behavior, we can also estimate from the roll step experiment. So if we simulate without taking into account drag, we get the gray lines. And if we simulate the same model, but including drag behavior, we get the red lines. And so the difference between them is actually the magnitude of the velocity induced drag. And it is, as we can see here, clearly non-negligible. What's also interesting to note is that for even velocities over 8 meters per second, this linear approximation is still quite accurate, which is also why this linear approximation is frequently used. So up to now, I've only shown data for step inputs on the different inputs. And so what we want to validate now is actually whether if we apply all of the inputs at the same time, if the simulations are actually accurate as well. Now for that, we did an experiment in which we have a very rudimentary MPC controller working. So it applies both roll, pitch, yaw rate, and throttle inputs. And then we simulated with the input data also a set of different model complexities. So in blue, we see the actual recorded data. And then in red, the model that I just presented. But then if we linearize this model, we get the black response, which clearly strongly overestimates the vertical thrust because of the small angle approximation. If we neglect the drag, then even for this very short response, because this is only 1.5 seconds starting from standstill, so even then, the no drag approximation even ends up too far ahead because it neglects the counteracting force. And lastly, if we neglect the battery dependency, so we assume that the battery voltage is equal to the nominal voltage, then in this case, in this experiment, the battery voltage was higher. And so the no battery dependency approximation actually underestimates the generated thrust, which makes the simulation end up lower than the actual measured data. If we then zoom in on the different quantities, then we can see, for example, for the yaw rate, that this transient behavior is captured a lot better than if we would just say that there's only a delay and then immediately the requested value is attained, which also shows in the yaw response. And looking at the roll response, for example, this transient behavior is also captured better. Not perfect because it's still an approximation, but it's still a lot better than if we would just say this is immediate with only a delay. So to conclude my presentation, we have a setup with a companion computer and the flight control unit that have an interface over which companion computer can send roll, pitch, yaw rate, and throttle references. And to represent the behavior of this setup, we developed a gray box model that trades off accuracy versus simplicity. All parameters of this gray box model are identifiable from flight data alone using realistic outdoor sensors. We proposed 3 simple maneuvers to gather the data for this parameter identification. And lastly, I showed the added value of nonlinearity, of including the battery dependency and of including linear aerodynamic drag. So thank you. This was my presentation, and I will gladly answer any of your questions.
Thank you, Matthias. Do we have questions? Please, Guido. Guido says that it's a cool work.
Thank you.
Says that some other work studies minimize innovation of a Kalman filter. And they say you optimize the discrepancy between your measurements and what you expect. He asks, what is the relation? Difference. Well, I will read. I think that it's probably better if we unmute Guido, because I don't get the question. He says some other work studies minimize innovation of a Kalman filter. You optimize the discrepancy between your measurements and what you expect. What is the relation difference?
Okay, if I understand the question correctly, then actually the question is, what's the difference between using least squares in this minimization or using a Kalman filter for parameter estimation? So in that sense, I would say this one is quite close, or for me, it's close to what I will actually be doing in a model predictive control context, where you you simulate your system over a horizon in the future using the nonlinear model, in this case also a fourth order Runge-Kutta system. So like this approach really is targeted towards evaluating or trying to capture the predictive qualities of the model. So we really simulate and try to get the full simulation over this horizon as good as possible, or as corresponding to the measurements. In a Kalman filter for parameter estimation, I think it's fairly similar, but in a Kalman filter, there's always a linearization step going on. Even if it's an extended Kalman filter, but then it's linearized around the current estimate.
I must say in the other work, they were optimizing the variances of the observations, and you are optimizing the model. So it's super interesting, I think. You also don't need ground truth in your case. It's the same actually for this other work, but so that, yeah, it's quite complementary, I think. I think it's quite nice. So thank you for your answer.
Thank you. I hope that that was a question that Guido was asking. I didn't get the question. I just read what he wrote. Okay, I have another question. You have your quad rotor and you have a kind of low-level controller. This configuration can be flight by someone using an RC control. He can fly the quad rotor.
Did I
yes,
understand your question? Yeah, sorry, maybe repeat your question, please.
Yes, you have the quad rotor and then you have a kind of low-level controller. And I asking if someone can fly this configuration with using an RC controller.
Yeah, sure. So basically, what we have is like where did I show this? Our setup has this.
That one.
Yeah. So we have this is the low-level flight controller, but this is running Ardicopter firmware. So basically, when you switch a mode, so we operate in guided mode, and in guided mode, this companion computer has the authority and can send input commands. But once we switch the flight mode to stabilize mode, then the control comes from a human pilot, actually. So
the human pilot is controlling a second order system, do you think? Because if he sends angles, so he's commanding a second order system. Yes.
Yeah, the human pilot, if he is flying in stabilized mode, he would be sending references to a system that always acts with a little bit of a delay and the transition. And this transition is what I show here, like can be modeled approximately as a second order system. Yeah.
Okay. Thank you. Do we have another question? I think that we have to end the session. Thank you to the presenters, and let's continue with the next session.
Thank you, Hugo. And let's continue with the second session. Of course, thank you to the speaker, Matthias. Very nice work. So now for the second session, Autonomous Navigation 1, we will have Israel Cruz Vega as the session chair. Israel, can you turn on your camera and your microphone, please? And if we have the first speaker of the session, please.
Hi, thank you very much, Dr. Martinez. Can you hear me?
Yes.
Okay. Okay, we will continue with the next session that is about Autonomous Navigation 1. Well, the first paper is motion-based named AV detection in GPS environments. So for the presenter, you have 15 minutes, please. So you can start now.
Okay, can you see my screen?
Yes.
Okay, and you can hear me correctly, so that's good. So yeah, good morning, evening, afternoon. So I'm Nado Drone, and I'll be presenting this work, which was performed by Erik Vroon, a student of TU Delft, who also worked together with TNO. Okay, apparently my slides have an automatic timing. So the objective of this work is to visually localize drones relative to each other inside swarms. And this relative localization is needed for collision avoidance, but also for swarm coordination. Now, typically what drones do in this case is that they exchange with each other GPS locations. But of course, in the urban canyon, these signals can be blocked. And of course, there can be also cases in which these signals are spoofed or jammed or distorted by multipath. Now, as an alternative, you can use vision and to relatively localize yourself with respect to other drones. And then there's two types. There's collaborative SLAM. So everybody makes a map and you join these maps and you localize into this general map, which is computationally quite expensive. Or you can try and detect the other drones. And this drone detection can be done in two ways. Either you add visual markers with infrared or ultraviolet light, for example, adding it to the drone, or you can try it without markers. And then there are some approaches with one camera that use, for example, optical flow or the appearance of other drones. But there's also approaches that use two cameras, in which basically, the stereo vision is used to detect other objects that are floating in the air. Now, today we will talk about using the optical flow for detecting other drones. And so why would this be interesting? Well, it's quite generic, more generic than appearance-based neural networks. Because if you train to detect the appearance of other drones, then you're kind of specializing to a specific drone that that is in your training set. But optical flow, with optical flow, you can basically detect any other moving object. Also, with a single camera, you may detect objects quite far. You see this image on the right, you see these cars also in the distance, for example. And possibly it's more robust against background clutter visually. So it may be that another drone is black, but and the background is also a bit black, but if it moves, then you can still see it because of the flow. And there's no additional hardware requirements. So sorry for my slides changing with the timer. Didn't do this before, but anyway. So the student, Eric, he evaluated different neural networks. What we see here is a drone. I don't know if you see my mouse. Let's do a laser. Yes, we see a drone. We tried out FlowNet, Raft, Mask FlowNet, and Light FlowNet. And so, yeah, as you can see already, this gives actually the nicest result, FlowNet 2, where these colors indicate the motion direction of the flow. And so he went with this, this flow. Now, in order to detect other moving objects, we make use of the property of optical flow, that if you're traveling to a point, so here we're an airplane, because Gibson is the researcher who introduced this optical flow. He worked with pilots. And if we're going to land on this landing strip, then the point where we're traveling to is going to have no flow. And all the other flow in the scene of static points in the scene will point away from this focus of expansion. Now, suppose that we have another drone that is moving to the right, and the flow will be different than if it was hovering. If it was hovering, then it would point like this. But now this drone is moving and its flow is different than we expect from the static environment. And so we see a difference in angle between the flow of the drone and the flow of the drone and the flow that we would expect if this drone would be hovering statically in the air. Now, this is the pipeline for the object detection. And so we have a video. We calculate optical flow with FlowNet 2. We derotate the optical flow. We'll go into the details in a second. We calculate the focus of expansion. We calculate this angle, so this difference between what we see and what we would expect from a static world point. And we threshold it. And as you can see already in this segmentation, we are stuck with some clouds here. So we actually also do sky segmentation to exclude these clouds. And then we're left with the drone. So now, derotation of the optical flow. Here we have the optical flow equations. Small u and v is the flow in pixels. And then these large letters are translational velocities of the observer, u, v, and w. And those form a translational component of the flow. And that's what we're interested in. But A, B, and C are the rotations. And the flow also has this rotational component, but we want to get rid of that. And that is why we make use of the gyros of the drone to derotate the optical flow. Now, when this is done, then we're stuck with the, then we're left with the translational flow, what we want. And then we need to determine this focus of expansion. So what we do is we pick two flow vectors, and then we try to find the intersection of where they come from. In an ideal case without noise, it would go exactly to the focus of expansion. And we do that a number of times, and because flow has some noise, of course, you get some statistics for these intersection points. And then we take the sample with most intersections within a certain radius. Now, if we have this focus of expansion, then we can look at these optical flow vectors. And some dynamic ones will be clearly different. So I have a big angle kappa. But some of them, it may be that a drone is moving exactly in the way in which we expect actually static flow to go. And that's, of course, a more difficult case for this method. Now, one more thing about thresholding on this kappa angle. This kappa angle should perhaps be different for large flow vectors than for small flow vectors. Because when you run an optical flow algorithm, it typically has a noise that is independent from the magnitude of your flow. And that means that the angle that is subtended by it is larger for smaller flow. And so you would like to allow for a larger kappa there. And here we see two different approaches. Like you could pick a fixed threshold independently of flow magnitude. And then this would be the same angle far or close. Or we adapt the kappa threshold based on the magnitude of the flow. And that is the image that we will see here. So we have the flow magnitude here on the x-axis. And we see indeed that the error in the flow, that this angle becomes smaller if you have a bigger flow vector. And we use this to make a fit. And we try out two schemes, one with a fixed threshold, like I said, and the other one with a dynamic threshold. It uses the white dashed line in order to determine which kappa to take as a threshold to say, okay, this is a dynamic point. Now, in step 7, we do sky segmentation. We use a deep neural network for this made by Tao et al. Which works really well. Now, what is our setup? We use AirSim. It's a simulator based on Unreal. We have camera view. We have depth outputs that we only use to determine ground truth optical flow. And we have a segmentation mask because we know where the drone is. It's here. It's actually hard to see in the image, I would say, in a still image. And so it illustrates why optical flow might be actually a good idea. Here we show what FlowNet 2 sees and what our ground truth gives, which shows that the ground truth is not an actual ground truth in the sense that we use the motion of the camera, we use the motion of the drone, we use the depth of the scene, but we don't take into account the clouds. And this is a main result. So we have the true positive rate. And so how many pixels of other drones do we detect? 1 is good, 0 is none. And then we look at what happens. If this kappa is big, it means that it moves in a completely different direction than a static flow. Or if kappa is small, which means that that the drone moves in a similar direction as the flow would be for a static point. And we obviously see that for small flow, we get quite bad results if kappa is small. But for bigger flow, actually the results stay very good. So it also depends on how quickly the other drone is moving. We also look at the fixed versus this dynamic threshold, where we set the true positive rate against, again, the flow magnitude. And we also have the false positive rate here. And the false positive rate is in green. And we see that, yeah, with a dynamic threshold, we have higher true positives, but we also have higher false positives. So yeah, to actually judge what is better, this is not conclusive here. But you can see that, for example, for the fixed threshold, we can get quite high true positive rate with a very low false positive rate. Now, I guess I've gone quicker than the presentation I would have done normally because of these timings, but okay, the recommendations. And so we now made a pipeline that's largely handcrafted, which feels a bit classic and traditional. And we hope it will mostly be benchmarking, used for benchmarking. Of course, we think that if you apply deep neural networks, you can get better results. It would be interesting to try out different inputs into the network. Images over time, optical flow, or even this kappa image, and see what these networks can do. Also, our current code is quite slow, and we actually use multiple networks. So we use one network for optical flow, we use another one for sky segmentation. So yeah, this is something that would have to be improved. And finally, this whole pipeline uses optical flow. So an advantage is that it can detect any other moving object. The disadvantage is that it detects any other moving object. And so we still need to see if this other moving object is a drone. And then it would be useful, of course, to also be able to determine a kind of distance. Now the conclusions, the motion-based object detector performed successfully, provided that kappa is large enough and the magnitude of the flow is large enough. And so AirSim was very valuable as a tool to make these image sequences. And we have also released the open source code for this. Now, as you can see, I thank you for listening. And if there's questions, I'll be happy to answer them.
Thank you very much, Dr. Guido. Let me see if we have questions. Okay, we have one question. How much do you depend on IMU? Would your method work for indoor scenarios?
Yeah, so how much we depend on IMU? We depend on the gyros to derotate. In this specific study, the AirSim simulator had quite good gyros, like almost perfect, I would say. Of course, in reality, you have some noise there, you have some biases, but we do notice that this derotation works relatively well. And so we think that also in a real drone, this would work. Indoors, outdoors, doesn't matter. And so we don't use any GPS or anything. So of course, the distractor objects are different. So outdoors, we have these clouds that are moving. Indoors, you may have people moving. So yeah, the challenges and the distractor objects are different.
Okay. Another question. Okay, can you tell me something about the delay process?
At the moment, not, because again, this was like Python code. I don't think that the student even profiled it. But I must say, for example, he was using FlowNet 2. You can also use more traditional, perhaps slightly quicker methods on a CPU. So like I said in the recommendations, we really need to work out this real-time component. And so in any case, if you use this method, you need dense flow. and that's going to take some time. On the other hand, yeah, dense flow is going to allow this segmentation of the object. And then it really depends on your hardware, how fast it will run. Yeah.
Okay. Well, there are no more questions. Thank you very much, Dr. Guido, for this
Thank you very much. Yeah. Okay.
Okay, so I think that we can continue with the next topic. Okay, the next step is about the framework and evaluation methodology for autonomous drone racing.
Hi, hello. There's an error in the program, so I switched places with the framework and evaluation methodology, which is from also my research group, and now I'm presenting the indoor Visual Semantic SLAM, improving VIO and RGBD for narrow spaces, if that's okay.
Okay.
Okay, you can hear me right and see me right?
Yes.
Okay, let me. Can you see the presentation?
Yes. Yes.
Okay. Do you want me to start, or shall I wait until?
I think you can start, please. Go ahead.
Okay. Well, thank you everyone for being here, for listening to this presentation. My name is, oh, I'm sorry. Wait, let me move this so I can move the slides. 1 second. I'm sorry. Yes, I was saying my name is Andres, and I'm going to talk about how we use OpenCV new camera, OCD, for indoor Visual Semantic SLAM and improving VIO and RGBD for narrow space navigation. So as an introduction, I want to talk a little bit about the motivation of the project. So we already know that aerial vehicles are nowadays practically essential in rescue work in catastrophe situations. And one example I would like to show, because it's quite recent, is the volcanic eruption of the island in La Palma here in Spain, which is actually happening right now, where drones have been very important in monitoring the volcano, wildlife, and of course people in general. Also, they can help with trapped people search, structure analysis, and thousands of other things we are aware of. But basically, what I want to say is that these type of vehicles can improve and complement rescue teams' capabilities, reducing the risk not only for them, but also for the people in danger. In most or some of these situations, global navigation satellite systems are available to help these vehicles to localize, but this is not always the case. So I think research on this topic is always welcome, and this is basically the motivation for the project. So the main objective we had was to provide MIVs or AVs with the ability to navigate in narrow spaces using lightweight and inexpensive visual sensors such as the OCD, which we will talk about later. We proposed two methods for estimating the position of the objects in space by extracting the centroid. And the semantic and spatial information extracted from these objects is then used in an SLAM algorithm to for loop closure. So also state-of-the-art object detectors and visual odometry are used along the proposed object detection methods for estimating the position. So the OCD camera from OpenCV has been used as the main sensor for this project. It incorporates 3 cameras, a stereo pair and a third RGB camera. The stereo pair has a lower resolution than the color camera, but incorporates twice the frame rate. And it also has depth and AI processing capabilities. and can run both in both monocular and stereo cameras neural inference. So also it incorporates an inertial measurement unit, an IMU, which we will talk about later, and weighs 115 grams. So first of all, why do we want to extract the centroid, and what is the centroid for us? The centroid serves as a representation of the position of an object in space. It also can represent or represents for us the geometric center of the object, or if we, as the simplification we do is like the centroid is the center of a box which surrounds the object. One advantage to use the centroid is that reduces the amount of information we have to store to locate an object in space, and also facilitates quite a lot the comparison with other objects, especially in terms of distances. One thing I would like to point out is that, for example, if we were to locate, if I ask you to locate the centroid of this object, a bicycle, it would be possibly around this gap here in the center of the object. So for us, it's quite easy to see this is the center, but in this kind of objects where the centroid is in a zone or in a place where there's a gap, the estimation of the distance to the object gets complicated, as we will see later. So just keep that in mind, that these kind of objects with gaps in the middle are a little bit more complicated to estimate. So the first step in acquiring the spatial coordinates of the centroid is to locate the target's object or objects that are captured by the cameras. So we used a pre-trained mobile net single shot detector. The whole computation of the detection is carried out in the OGD camera, which is one of the advantages of using this camera. And the inference can run on both the stereo pair and the color camera. So when the object is detected, the detector surrounds the object with a bounding box, and we set the centroid at the intersection of the two diagonals of the rectangle, obtaining then the geometric center of the bounding box. So the first approach, the first proposed method for centroid extraction is based on the use of the color camera and the depth map that the camera can calculate by default. And the process is briefly, or the proposed algorithm is briefly summarized in this slide. First, the object detector is applied to the RGB image. Then the depth map of the image, the whole depth map, is calculated. Then the bounding boxes are located, which were previously detected by the object detector, are located in the depth map. And finally, the depth of the center of the bounding box is extracted, and the X and Y coordinates are calculated from that depth. This approach has two major problems. The first one is that the whole depth map needs to be computed. And the second one, and maybe the most, the bigger problem, is that this, as we said, if the center of the bounding box is located in a gap of the object, such as in the bicycle example we saw just before, the depth measurement is not reliable, since we would be getting the depth of the background, not the object. So for solving this issue, we propose another approach which will solve these issues. So the approach takes advantage of the stereo pair. The aligned axis pairs stereo 3D model is applied, and the bounding boxes extracted in each image serve to calculate the disparity. With this disparity, we can obtain the depth of the two diagonal corners of the bounding box, which in our case, again, this is a simplifications, are equal. We can make these simplifications since the cameras are very, very close and in the same plane. So for better understanding, we can imagine that the bounding box acts as a parallel plane to the camera that cuts the object vertically through its center. And that's where we place the centroid, or where we suppose the centroid is. So in this next slide, we can see a very briefly simplified process of this approach. First, the object detector is applied to both rectified images. We run two neural networks in parallel to both rectified images. And in a second step, consecutive filters are applied to correctly match the bounding boxes of each image. This is a very important step because if we wouldn't match correctly the bounding boxes in the image on the left with the bounding boxes in the images on the right, we would basically we wouldn't have reliable measurements. So some lightweight, talking about computational load, filters are applied based on their relative position, their area, and their aspect ratio. The depth of the center of the bounding box is calculated as the average of this depth of the corners we calculated. And then finally, again, the X and Y coordinates are calculated using the 3D, the axis pair 3D stereo model. So to take advantage of the camera's capabilities, our intention was to use a visual planar semantic SLAM algorithm proposed by Rida with some modifications. This algorithm proposed by Rida is a graph SLAM based algorithm that uses RGBD camera to extract depth pixel information. And from this data, it extracts flat surfaces of the objects. So with this information, it can calculate the centroid of the object, and the normal orientation of the obtained plane based on the density of the point. Of the points. This approach has one major problem, and it's again that it does not work with every shape of object. For example, objects with gaps or objects that do not contain planar surfaces don't work well with this approach. So our proposal was to modify the system a little bit to use both of the previous methods we talked about with the AOC. Now the centroid is calculated directly on the camera, and the plane extraction has been removed completely. So this reduces the computational load significantly on the onboard PC. Since before we had to make the calculations of the centroid in the onboard PC, now we can do the calculations in the camera, and the centroid is directly extracted from the camera. These changes has one major improvement only in the second method, in the stereo approach, and that is that it allows reliable measurements to be obtained without depending on the shape of the object, whether if the object is hollow, it has gaps, or doesn't have any planar surfaces. So in order to determine whether odometry can be improved and which of the methods is most suitable for navigation, we ran different experiments where we navigated in an indoor environment full of common objects such as monitors, chairs, tables, bottles, and making several turns to generate loop closures. As I mentioned before, the OGD has an MIU. However, we couldn't find enough, it doesn't have enough capabilities to be used as a trustful or confident odometry source. So we used instead the InterRealSense D265 with loop closer disabled, of course. In addition, a motion capture system was used in order to compare the algorithm performance against the ground truth data. So for the results, as shown in the table, the object position estimation using the RGB image approach is not capable at all of improving the road pose estimation. Actually, on the contrary, it makes it worse. However, the stereo approach is able to correct the trajectory, reducing the absolute trajectory error in around 0.16 meters. So as conclusions for this project, I would like to mention that we have proposed a possible usage for the new OpenCV camera. From our tests, we have seen that the color camera approach or the RGB camera approach works best at detecting objects which are not hollow when they are far. while the stereo approach provides better results when closer distances. Talking about closer distances are from 0.2 meters to 1.5 meters, and far, we say around 1.5 meters to 2.5 meters. Also, the stereo approach has shown its capabilities to improve the odometry data, while the other method is unable to improve estimation. The main reason for this, although we didn't use much difficult objects, is that in the RGB approach, we are using a higher resolution image, and also we are computing the whole depth map of the image. That means that the computational load is higher, and the FPS of the image drop quite significantly. We have to keep in mind that when the camera is moving, when it's mounted on a drone, or even if we have it by hand and we move it and it's not so fluent, the object detector has some trouble detecting objects accurately, and what is more important, drawing or detecting a bounding box correctly around the object. So that's why basically, due to fluently and lower computational load, the stereo pair works much better. So also note that the OOCD is still under development, and we hope to see some improvements, especially in FPS and the IMU, being this last one really important and for robotics and SLAM applications in general, or drones applications, where it's much more convenient to have a camera which also includes an IMU. And basically that's all. I will be happy to answer any questions as best as I can, and thank you for listening.
Okay, thank you very much, Andres. Let me see about the questions. Okay, here is one question. What is the speed of your CNN output running on the OAKD?
Okay, sorry, I didn't understand the question.
What is the speed of your CNN output running on the OKD?
I can't answer that question because I actually don't remember. So on concrete data, I don't have. It's been a long time since the project, so I don't remember the exact data. I'm sorry, I cannot answer that question. I'm sorry.
Okay.
But what I can say is that that output we talked about the CNN, the neural network, I mean, is not a bottleneck at all in the system. The bottleneck we would have in the filter stage, and that's why we used very lightweight filters, because matching the bounding box in each image is the most computational expensive load of the whole process. So if you were wondering if that's the bottleneck, it wasn't.
Okay. I have another question. How much extra computation does the detection of objects cost, and how does it relate to the cost of other parameters that may be changed to improve accuracy, like tracking more features or something like that?
I don't know if I understood the question correctly. Could you summarize it or reformulate it, please? Or
about the extra computation for the detection of object cost.
Yeah, so basically, I guess this ask about what is what we talked about, maybe the bottleneck, or what would be the most computational costly in the system. I guess this is where it goes, the question.
Sorry, I was reading another.
Yeah, I mean, if the question is about, I cannot read it, I don't know where the question is, so I think the question is about what is most costly in the system, or something like that, or...
Okay, I will read again the question.
Okay.
How much extra computation does the detection of objects cost? And how does it relate to the cost of other parameters that may be changed to improve accuracy, like tracking more features or something like that?
Okay, yeah, so as I said, maybe the bottleneck would be to filter or to match the bounding boxes. So for example, if you would use an algorithm like SIFT, which is very computational resource expensive, but would bring us very good results, this would mean that the object detection would be really fast, but however, you would spend lots of time matching which bounding box corresponds to which bounding box. So as I said, the object detector is not the bottleneck at all. It would be the matching algorithm of the bounding boxes. That's and for example, if you talk about tracking more objects, if we would detect, for example, 100 objects in one image, this filter would spend more time, so it would be much more computational effort for the camera. And so yeah, the more objects you need to detect, not because of the detector, as I said, but because of the filters, would be or the matching algorithm would be more more costly, talking about computational resources. Yeah.
Okay, thank you very much.
Thank you.
Okay. So I think that we don't have any more questions.
Okay, thank you very much.
Okay, thank you very much, Andres. Okay, so we can continue with the next presentation. And this is about a compact approach for emotional assessment of drone pilots using BCI. Okay, Daniel, you have 15 minutes, please. You can start now. We can hear you, Daniel. Are you using your microphone? Hi, Daniel.
Hi.
Okay, Daniel, we can hear you.
Sorry.
Now you can start, please.
Can you see the presentation?
Yes.
So, hello everyone. Thank you so much. I'm so happy to be here participating in this conference. My name is Jesus Daniel Olivares Figueroa. I'm a PhD student in the National Institute of Astrophysics, Optics, and Electronics. This project is titled A Compact Approach for Emotional Assessment of Drone Pilots using BCI. As you know, recently drones for different applications such as civil and military service have been increased. So some of these applications require the drone pilot to be focused. So emotional states such as stress affect the performance of drone pilots, especially when handling an emergency situation. There are different methods for measuring human stress. For example, subjective methods use questionnaires or interviews, while objective methods use physical measures. In this case, we will focus on brain activity. For years, neuroscience has shown that the response of the human brain is affected by stress. Non-invasive technologies are the most common sources to study brain activity. However, EEG is a preferred application in many research areas due to technological advances and commercial availability. But even though drones are one of the most versatile tools nowadays, there are now studies that specifically focus on measuring the emotional states of drone pilots, especially when handling an emergency situation. This motivated us to propose an intelligence system to continuously monitor the emotional states of the drone pilots. We think this will considerably reduce the risk of an accident occurring and will give a greater safety for the pilot. Our main objective is to create a brain-computer interface, or BCI, in a simulated environment as a first approach to monitor the emotional states related to the performance of drone pilots. We have been exposed the drone pilots to situations with different levels of mental workload, and we have analyzed the brain response with EEG signals. Therefore, we have created a graphical user interface to control the experiment and link it to the application Emotive Pro to generate a database with information obtained from 3 subjects. In this case, we have induced 3 emotional states: quiet, tense, and very tense. For the experiment presented here, we have selected quiet and very tense groups for the classification process. To separate the brain signals, we have used a minimum order filter to obtain the alpha and the beta rhythms. And we use standard classifiers, k-nearest neighbors, or KNN, and support vector machine, SVM. And finally, we developed a system capable of pre-processing, feature extraction, and classification of the signals in real time in a simulated environment. This because it's our first approach. To get into context, I will explain the main theoretical fundamentals. A BCI is a system that measures brain activity. The general process of a BCI is presented here, where we first acquire the signal from the headset, and every channel is pre-processed to extract the features of the clean signal. Then in this case, the features are used to classify the signals to translate as a common signal to the next, to an application. So the EEG is a non-invasively technique to explore the brain electrical activity. The signals that we obtain are called brain waves. But the main disadvantage is that these signals are affected by noise generated within the brain or on the scalp. This type of noise is commonly known as artifacts. The EEG signals that we obtain are classified depending on the brain rhythms and the brain regions that they occur. In this case, we will focus on the alpha and beta rhythms in the frontal and temporal lobes. The Symmetry Index, in this case, is used as the main feature because it's related to the change in the emotional states in response to different stimuli. To calculate this feature is really simple. We obtain the power of one electrode on the left lobe and another one in the right lobe. Then we obtain the difference between these 2 powers. To pre-process the signals, we first apply the empirical mode decomposition to obtain the different levels of energy of one signal. These signals are called intrinsic mode function, or IMFs. We have used AMD to remove the DC component, the artifacts, and presented in the lower frequencies. Also, to pre-process the signal, we use independent component analysis, or ICA, to separate the sources that correspond to physiological signals that corresponds or maybe to artifacts also. The estimated sources that we obtain are called independent component. So as I mentioned before, classifiers that we use are the k-nearest neighbors and support vector machine. This is the device, the Emotive Pro, that we use to record the EEG signals. It has 5 channels, as you can see here, 2 for the frontal lobe, another 2 for the temporal lobe, and the last one channel to the parietal lobe. It has a sample rate of 128 Hertz and a bandwidth from 0.5 to 43 Hertz, and has a digital notch filter at 50 and 60 Hertz. This is the representation of the experimental development environment. From the first screen, we control the experiment. This is the graphical user interface that we have created. And from here, we send the labels to the app and instructions to the second screen where the pilot performed the flight task. As I mentioned before, the drone pilots were exposed to three emotional states that were divided into 3 levels. For level 0 corresponds to the quiet states. At this level, the subject performed basic maneuvers such as flying forward or backward, without obstacles. And in level 1 or tense state, the subject must run the tracks with obstacles. Subjects were instructed to complete the tracks by trying to beat their own record. Each time they repeated the same circuit. And finally, the level 2 corresponds to the very tense state. The subjects perform the same task as level 1, but this time were distracted by auditory and visual stimuli. This is the general scheme of the simulation of the real-time processing of the signals obtained from the database. The algorithm captures each sample of the signals, and once the vector reaches a certain leg, it begins to remove the DC component, the trend, and the artifacts. Within this stage, we first apply the AMD to remove the residual and use the IMFs with the lower frequency to trend the signal. These steps are repeated for each channel, and subsequently we apply the independent component analysis. These independent components are used for the artifact removal. The main idea of this step is to calculate Gaussians on the outliers of the signals. These signals, the blue signal, corresponds to the absolute value of the normalized independent component. Then to calculate Gaussians are subtracted from the signal, and it's reconstructed, as you can see here, to recover the independent component with the removal of the artifacts. This process, in this step, is repeated for each independent component, and finally the signals are reconstructed with the inverse process of the independent component analysis to obtain the EEG signals that with the reduction of the artifacts. So signals are then filtered to obtain the alpha and the beta rhythm. And then we calculate the frontal, temporal, and total asymmetry index for the alpha and the beta rhythms. And these equations are stored as a vector. For the 3 vectors, we measure 8 statisticals to obtain 28 features in total for each brain rhythms. These features were used by the following algorithm to train the KNN and the support vector machine classifiers. With the algorithm, the step and the window size were varied to calculate the features of the vectors that contain the asymmetry index. And several models were trained for each step and window size in this step. We repeat 20 times. And in each execution, the training and test set are randomly selected, and different hyperparameters were tested depending on the type of classifiers. Also, models are evaluated in their training and testing stage with accuracy, precision, sensitivity, and specificity. And finally, the mean of the 4 metrics was calculated to select the KNN and SVM hyperparameters with the best average for each step and window size. This results corresponds to the best average obtained from the four metrics. It is observed for all subjects that regardless of the window step considered, the results tend to improve as the window size increases, as you can see here. The best performance for the three subjects is typically obtained when the window step, is 10 seconds for both classifiers, as you can see here. For this is repeated for each subject, for subject 1, subject 2, and subject 3. We can see that the results are very similar among the classifiers. And also comparing the alpha and the beta rhythms of the different steps and window size, we can see that generally observed that the beta rhythms is higher than the alpha rhythms. As you can see for the subject 1, for the subject 2, and for the subject 3. The table shows the best results and the hyperparameters calculated in both classifiers for the alpha and for the beta rhythms. We observed that for the KNN classifiers, the best results are obtained using 3, 4, and 5 nearest neighbors. This favors the real-time application objective of our study, since the smaller the number of nearest neighbors, the shorter the time required for the classification. The delay, also we measure the delay for each execution for the artifact removal and the rain rhythm filters. We obtain a delay average of 0.02 milliseconds, as you can see here. So a BCI application based on EEG has been proposed to continuously monitor the emotional performance related to the emotional states of drone pilots. We built a database with the quiet and very tense states to classify using the k-nearest neighbors and support vector machine. And our finding shows that the results is a clear, there is a clear separability between these two groups. The delay generated by the algorithm for automatic real-time artifact removal meets the condition of this project for its real-time application. However, it must be optimized for better elimination artifacts. We found that the alpha and that the Symmetry Index is an excellent feature related to the emotional response in drone pilots in situations of emotional tension. Our study suggests that the results show better performance when using the beta rhythms, comparing these to those obtained from the alpha rhythms. However, even though our result looks great, more testing is needed to reach stronger conclusions. Our next step is to improve the most important stage that were presented in this presentation. As future work, we have raised the following points: to optimize and explore other preprocessing techniques to apply them in a real time, to explore the rest of the brain rhythms, to explore sophisticated classification techniques, to expand the database in a real drone application. I think this is the most important, and make it publicly available. To implement the classification algorithm in a real system using intelligent algorithm to make our system more robust. And well, I think this is all. Thank you so much.
Okay, thank you very much, Daniel. Let's see if we have questions. Okay, did you try to use another classifier technique like deep learning?
Yes, we are planning to use deep learning to classify the signals.
And why didn't you use it?
Sorry, I can see. Can you repeat me the question?
Why did not you use deep learning?
Because we think that we can extract the characteristics and skip the process when we use in the presentation. I mentioned that I have to extract some features. We think if we use deep learning, maybe it will be better and faster once we have the model.